Students, now we are going to proceed ahead with another very important concept in successive differentiation, which is called as the Leibniz Theorem. Now we remember there is something called as a product rule in a differentiation. If you have y is equal to u into v, then dy by dx is given to us as v du by dx plus u dv by dx. It simply means that if there are two functions which are multiplied with each other, then their derivative is given to us as, we keep the second function as it is and we differentiate the first function, then plus sign, then we differentiate the second function and we keep the first function as it is, isn't it? It is something like this: second function as it is, derivative of first function, plus first function as it is, derivative of the second function. So this is what we call as a product rule. So here you have got the derivative of first order. So now if I have two different functions u and v and they are multiplied, and now if I need yn, that means the nth order derivative, how do I get it? So this is obtained by using the Leibniz theorem. So let's understand what is the Leibniz theorem. Students, now I have two different functions u and v. Both of them are functions of x. So I can say y is equal to u into v. That's my first equation. So here u and v are both what? They are both functions of x. Nobody is a constant here. Both of them are functions of x. So I'm going to differentiate both sides. Let's differentiate both sides with respect to x. So I'll be getting y1, isn't it? So y1 is the first order derivative. So y1 becomes equal to, the second function is v. So v as it is, derivative of u. So I can write du by dx. But I know the first order derivative can be now denoted as u1. So I'll be writing v u1 plus u into v1, the first function as it is, derivative of the second function. So u is as it is, derivative of the second function, that's v1. So I'm going to call this as equation number 2. So now I have got y1. I need to reach till the nth order derivative. That means I should keep on differentiating the functions ahead, isn't it? So now if I differentiate again, let's differentiate again both sides with respect to x. So y1 is nothing but dy by dx. Its next derivative will be d square y upon dx square. So that is going to be called as y2. So I can write here y2 is equal to, now observe carefully, let's focus our attention on the first term here. There is v, there is u1, isn't it? So v into u1 is what I have now. V is a function of x. u1, which is the first order derivative of u. Since u is a function of x, its derivative will also be a function of x. Let's take an example. If I ask you derivative of sin x, derivative of sin x comes cos x, which is again a term of x. That means if you have that u is a function of x, then u1 will also be a function of x. So the derivative is going to look something like this. So let's take v constant, isn't it? Let's keep v constant, derivative of u1. So derivative of u1 is going to be u2. Getting on what? So u1 stands for the first order derivative. u2 will stand for the second order derivative. Then first function as it is, derivative of second function, plus second function as it is, that means u1 as it is, derivative of the first function. So derivative of v is going to be v1. So that was the derivative of the first term v into u1. Then plus sign, and now you take u into v1. So u into v1. Now I want to differentiate. So here also I'm going to keep one function as it is, I differentiate the other function, and then I reverse the order, isn't it? So here let's keep v1 as it is. Let's keep v1 as it is. So I'll differentiate u, so derivative of the first function, second function as it is. So I write u1 into v1, isn't it? v1 is kept as it is, derivative of the first function. Then plus, now the first function as it is, that means u as it is, derivative of the second function. So the derivative of v1 is going to be v2. So this is the derivative of the second term, isn't it? So observe carefully. Can you see there is u1 v1 and u1 v1 present two number of times? So will my derivative y2 look like this now? It is going to be v into u2 plus 2 u1 into v1 plus u into v2. I'm going to call this as equation number 3. So that's y2, students. I've got a second order derivative. I'm going to go for one more step now. I'm going to get y3 also, and then I'll be generalizing for yn. Let's see what y3 comes. So again, I'm going to differentiate. So I'll write here differentiate again both sides with respect to x. So now if I differentiate again both sides with respect to x, y2 is simply going to become y3, isn't it? The next derivative, the next order derivative is y3, v into u2. So this is one function, v into u2, so I keep v as it is, isn't it? Let's keep v as it is. Derivative of u2 is going to be u3. You want to keep on getting the subsequent derivatives, getting or not. So v derivative is v1, v1 derivative is v2, then v3, then v4, and so on. The terms will keep on coming. This v1, v2, v3 or u1, u2, u3 are nothing but what? They are the first order, the second order, the third order derivatives of the given function u as well as v. So u2 is actually d square u upon dx square. So that idea must be always very clear in the mind. u2 is nothing but d2u upon dx square. This y2 is nothing but d2y upon dx square. So all these terminologies must be very clear in the mind. So students, now tell me, this is v, this is u2. V is a function of x, we know. u2 is also a function of x, because again, if I give you y is equal to sine x, I ask you the first derivative. The first derivative is going to be cos x. If I ask you the next derivative, the second derivative, it is going to be what? The derivative of cos x is minus sine x. So are you observing that the function of x is getting retained? Derivative of sine x comes cos x, derivative of cos x comes minus sine x. Again, if you go further, if you get the derivative of minus sine x, it is going to come minus cos x. So if you keep on differentiating further and further and further to a function of x, it will always keep on evaluating the functions of x, getting or not. It will always give the answers in terms of x. Even if you take a constant function, for instance, let's take x square. X square, the first derivative is 2x, isn't it? The next derivative is 2, which is a constant term. But can you write 2 as 2 into x raised to 0? So 2 into x raised to 0 is nothing but what? It's a function of x, you can say. Again, if you differentiate 2, the derivative of 2 is 0, but I can still write 0 as 0 into x raised to 0. So every single time, even the answer comes 0, I can say 0 can be treated as a function of x. So if you have a function of x and if you keep on differentiating for n number of times, you will always get a function of x. So students, here v, the first function as it is, derivative of u2. So the next subsequent derivative of u2 is u3. So this was u into v rule. I am applying the u into v rule, the product rule. So it says that if the first function is kept as it is, you have differentiated the second function, then you should write one more term plus second function as it is. So u2 as it is, derivative of the first function. So that's u2 into v1. Likewise, that was a derivative of the very first term, isn't it? So let's now focus our attention on the second term now. Now be very careful. The second term has a constant or a coefficient over here present, that is 2. So this 2 will be kept outside the bracket, because u1 into v1, I am going to make use of the product rule, and the product rule always gives us multiple terms. So u1 into v1. So how the terms are going to look like here? So I will say that derivative of the first term, I get u2, second term as it is, second function as it is, plus first function as it is, derivative of the second function. It is very simple. I'm simply applying the product rule. It says keep one function constant, differentiate the other function, then plus you reverse the order, isn't it? Now you take the second function as it is, differentiate the first function, or differentiate the second function and keep the first function constant. So it simply changes the order, that's all, isn't it? So whenever you are using u into v, it simply is nothing but what? Take one function as constant, differentiate the other function, then plus then you reverse the order, isn't it? So here what I did was I differentiated u1. Its derivative is u2. So that time v1 was kept constant. So second time I should keep u1 as constant and differentiate v1. So derivative of v1 is going to be what? It is going to be v2. So that was the answer of derivative of u1 into v1. Then students plus now again u into v2. So here also I'm going to differentiate. So differentiation of the first function, second function is kept constant. So I write u1 into v2, isn't it? u1 into v2, and then second time I'll be keeping the first function as it is. So u as it is, derivative of v2, that's v3, isn't it? So now let's simplify the terms. Now observe carefully, there is this term u2 into v1. There is another term u2 into v1. It is accompanied with the coefficient 2. So that's u2 v1, u2 v1. Likewise, I have this u1 v2. So here also I can see there is u1 v2. So I will be again very careful with this term. It is accompanied by 2. So now students, can you tell me what y3 is going to come? So I can say y3 is going to be equal to, so the first term is v into u3, then plus 2 u2 v1, 1 u2 v1. So that's 3 u2 v1, 3 u2 v1 plus students 2 u1 v2. So that's 3 u1 v2. And finally, the last term is plus u into v3. I would call this as equation number 4. Now observe carefully. I hope you must be definitely recalling the Pascal's triangle. If you recall the Pascal's triangle, it is given something like this. We write 1, 1, isn't it? Then 1 plus 1 is 2, and we again add 1s on the other sides, the either sides, left and right, isn't it? Then 1 plus 2 is 3, 2 plus 1 is 3. Then again we add a 1 on either sides. So now observe carefully. Look at this y2, the second order derivative. You can see that the coefficients are what? 1, 2 and 1. Observe here, 1, 2 and 1. Look at the next order derivative, that's y3. So that's equation 4. The coefficients are 1, 3, 3 and 1. So there is 1, 3, 3 and 1. So are you observing y1, y2, y3? These are actually obeying the Pascal's triangle, isn't it? So if I now proceed for y4, what can I say? For y4, I will definitely get 1, 4, 6, 4 and 1, and observe carefully how I'm going to write y4. So students, if I want to get y4, now again you observe one very specific pattern that is getting followed over here. Look at y3. Its first term is u3, isn't it? It contains u3. Then there is u2, then there is u1, and finally you can see u. So it started from u3 and it is continuing till u, or I can say u0, isn't it? So u1, then this is u0. Likewise, observe the terms of v. This is v, isn't it? v0, you can say v0, v1, v2, v3. So are you observing that u is descending and v is ascending? So if I want to write for y4, how would I write it? So y4 can simply be written as, so I'm going to start with u4. Look at this, y3 started with u3. Look at y2, it started with u2. Look at y1, it started with u1. That means definitely y4 is going to be starting from u4, and then I will keep on descending the terms. So y4 can be written as u4, u3, u2, u1, and finally I can write u, isn't it? So you can observe 4, 3, 2, 1, and this is 0th term, u0, or you can simply write it as u. So now u is descending. What happens to v? The other term v is going to ascend. So it starts from v here. So I write v, then I can write v1, then I can write v2, V3, and here I'll be getting V4. So I'll write this V over here. This is U4 into V. And then I simply want to fill up the numbers of order 4, isn't it? For power 4. So that's 1, 4, 6, 4, 1. So 1, 4, 6, 4 and 1, and in between I will simply put a plus sign. So that's why 4. So are you observing here that the fourth order derivative is nothing but very similar to the expansion of a plus b raised to 4. If I ask you to get a plus b raised to 4, how would you get it? You write a raised to 4, then you write a cube, then you write a square, then you write a, and then a raised to 0, which is taken as 1. Here u raised to 0 is not taken as 1, or u0 is not taken as 1. It is taken as u itself, the function itself, because this is not expansion of a plus b. It is nothing but the product rule. So that one function has to keep on repeating over there. The u will always stay there. So u into v says what? First function as it is, differentiation of the second function. So the one term is always kept as it is, and to differentiate the other term. So here this u has to be retained at the end. And likewise you can observe that for v it is ascending, the terms are ascending. So in general students, can I now find yn? I can see that it is definitely following the Pascal's triangle. So if you remember the binomial expansion, you got to remember your binomial expansion. The binomial expansion comes something like this. So that is what I'm going to make use over here, because this is exactly obeying the binomial expansion. Look at y4, look at y3, look at y2, look at y1. They are all following the Pascal's triangle. That means if I keep on proceeding further, I will definitely end up on the binomial expansion. The last term, the nth derivative, is definitely going to come looking like the binomial expansion. So you need to be first of all very much aware of the formula of binomial expansion. So let's see what it is. I can say a plus b raised to n. We know a plus b raised to n can be written as nc0 a raised to n and b raised to 0, then plus nc1 a raised to n minus 1 into b raised to 1, and then plus nc2 a raised to n minus 2 into b square, then plus nc3 a raised to n minus 3 b cube. Let's write one more, nc4 a raised to n minus 4 b raised to 4, and plus dot 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 till the last term, which is going to look like ncn a raised to 0 and b raised to n. So that's the formula for a plus b raised to n. This is one of the ways in which you can write the binomial expansion. Now watch this again carefully. There are formulas available for this nc0 and ncn. They are both 1, isn't it? They are both 1. We have the formula of NCR from permutations and combinations. So NCR, we remember it is n factorial upon r factorial, n minus r factorial. So you can make use of that formula over here to get all these values. So if you try to get the value of NC1, it is going to be n. Likewise, if you get the value of NC2, it is going to be n minus 1 upon 2 factorial, and so on. You can keep on getting the terms. So again, this a plus b raised to n can also be written in a different way. So let's write a plus b raised to n one more time. So as I said, nc0 is going to be what? It is going to be 1. So my answer is a raised to n, b raised to 0, plus nc1 is n, a raised to n minus 1 into b, plus n minus 1 upon 2 factorial, a raised to n minus 2 b square, plus n minus 1 n minus 2 upon 3 factorial, a raised to n minus 3 into b cube, plus n minus 1 n minus 2 n minus 3 upon 4 factorial, a raised to n minus 4 b raised to 4, and so on. The terms will keep on coming till the last term, a raised to 0 and b raised to n. This is the simplified form of the binomial expansion. Now how do I get yn, students? It is very simple now. So I can simply get the value of yn, that is the nth derivative. This is called as the Leibniz Theorem. So how do I get it? Observe carefully. What did I tell you? U is descending. U4, U3, U2, U1 and U. So here also U will start descending. That means I will first get what? I will get UN. That's my first term. What will be the next term? The next term is going to be UN minus 1, isn't it? What would be the next term? Again, you descend by 1, you get UN minus 2, UN minus 3, and so on. You will keep on continuing, isn't it? So on, you will keep on continuing till the last term, which is simply going to be U. That is very important. It is not U0. It is U0. That means it's the initial term. So you get simply U. Likewise, what happens to V? It is ascending. So you will begin from V. So U1 into V, then you get V1, you get V2, you get V3, and so on. You will keep on continuing till Vn. Now you got to understand V, that means it is a function kept as it is. V1 stands for the first order derivative, V2 stands for the second order derivative, V3 is the third order derivative, Vn is the nth order derivative. Same thing is true for Un, Un minus 1, Un minus 2, and so on. So the suffixes which are written over here, they indicate the order of the derivative. This is very important. So now students, I've got Yn. I need to fill up the coefficients over here. That is an easy task, isn't it? You just look at the coefficients which were present over here. So you have the very first coefficient as n. The next coefficient is n minus 1 upon 2 factorial. The next coefficient is n minus 1, n minus 2 upon 3 factorial, and so on. It will keep on coming till the last term. You need to now simply fill up the plus sign, isn't it? So I can write plus and dot 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 till the last term, U into Vn. So this formula is called as the Leibniz Theorem. Now students, there is absolutely no need to mug up this particular formula. Just understand it conceptually. What does it say? It simply says you begin from the very first function, its nth derivative. Take first function, there is U into V. Understand very carefully now. There is U into V. So there is the first function U. The second function is V. So you begin with the nth derivative of the first function. So you start from Un, isn't it? And you keep on descending down by one derivative each time, Un. Then the next one is Un minus 1. The next one is Un minus 2. So you keep on descending the derivative of U and keep on ascending the derivative of V. You begin from what? Begin from V, then V1, then V2, then V3. That means you're ascending the derivatives of V and you're descending the derivatives of U, and you need to fill up the coefficients. The coefficients are simply filled up by what? 1, n into n minus 1 upon 2 factorial, n minus 1, n minus 2 upon 3 factorial, and so on will keep on coming. Look at this. This is the second terms. This is the second term. Look at this coefficients. 1, 1. So that's n. Look at this. 2, 2. So there are 2 terms upon 2 factorial. 3, 3. You have 3 terms upon 3 factorial. So this is how you can easily remember the formula conceptually. There is no need to mug up, isn't it? So take U, keep on differentiating from nth order and keep on descending by 1 every single time. Take V, first time it is kept as it is, and then keep on ascending its derivative till the nth term. So students, this is what the Leibniz theorem is. You got to memorize what the formula is. On the contrary, I should be saying like this: instead of memorizing it, you understand it conceptually, so that when it comes to solving the questions, you will be very comfortable in applying the Leibniz theorem. So students, that was all about the concept of Leibniz theorem. Now we are going to proceed ahead with some examples based on this particular concept.